All right, welcome back everybody to the last talk of this afternoon session. It's a pleasure to have Chile who's a researcher at Princeton University. Chi, take it away.
Okay, thank you for the introduction. So today I'm very happy to be able to talk to you about some of my recent thoughts on domain adaptation or handling distribution shift in general with label propagation. And this is joint work with my wonderful collaborators. And this talk is based on two of these papers. Okay. Nowadays, with the tremendous development of machine learning, people are eager to apply the technology to real-world scenarios like autonomous driving, healthcare, and the robotics. However, in real deployment, people often see failure cases that prevent us from expanding their usage because people won't trust our models with those failure evidence. So what is the problem? Why do our model fail in real life, even though I'm sure they have been tested extensively in simulation and other testing scenarios? One problem is that the machine learning models tend to be non-robust. Not only to non-robust to adversarial attacks, which is one of the theme of this workshop, but also to distributional shift. And this is the focus of this talk. And another problem is that they can be unprincipled. This means there are not enough theoretical analysis to support much of the existing work on handling distributional shift. And we would need more theory to help us understand the working scenarios of existing work and guide us towards better algorithm designs. So in this talk, I will first introduce different kinds of distributional shift and discuss a little bit of the prior work. And I will introduce a new method. It is not entirely new, but there are certain innovations and differences in the proposed algorithm. And I will propose some theoretical analysis of that, followed by some empirical validation. And one important part of this new algorithm is that it is designed on the representation space that satisfies some certain good properties. And I will talk about that in the end. So first, let me introduce different types of distribution shift. So in general, distribution shift means like when we have the input signal X and the label Y, their joint distribution has changed from the source domain where we train our model to the target domain where we test our performance. And there are different types of distributional shift. For example, covariate shift means that the marginal distribution are different in the source and target domain. While the relationship between Y and X or Y given X remains unchanged. This is still very challenging, even though the difference only comes from the marginal distribution. For example, here, you can see that in the source domain, we have the labels or the data from the two classes. Well, a simple linear classifier might be able to distinguish them. But when you try to extrapolate it to other regions you haven't seen, it is very possible that since you haven't seen the other regions, your previous predictor is entirely wrong. And there are other types of distribution shift, like modal shift, even the conditional distribution of Y given X has changed, or label shift, which means the probability of Y are different. Our focus will be on covariate shift. And covariate shift is ubiquitous phenomenon. For instance, in this brief dataset, you can see that with the source domain, even though they are all birds, it's possible in the source domain they have more like green land background or water background, while in the target domain they have sky background. So they have different marginal distribution. However, whether this image is a bird or a table whale or some other labels is associated with the image semantic meanings or not the environment. Therefore, in these examples, I believe we only need to tackle the issue of covariate shift, while the relationship between the label and the image has not changed. And the target specific in this talk is to design some principled way to handle covariate shift with some additional information, because without any additional information, there's no way we can handle covariate shift. And we assume that we have additional unlabeled samples from the target domain. So since I mentioned that this phenomenon is ubiquitous, there have been extensive studies on handling covariate shift. The list is very inexhaustive, but I just want to discuss a little bit. One of the most traditional methods should be like importance sampling. So instead of like minimize or like the empirical risk minimization on the unweighted summation of the loss function on each samples, here importance sampling will just reweight each sample with the density ratio from the target domain and the source domain. And the motivation is very straightforward. It wants to like reduce the selection bias of all the samples. But there are a lot of caveats here, because first, it will require that the support of the target domain to be contained in the support of the source domain. Otherwise, this value can explode to infinity if there is certain sample that we only see from the target domain but never seen from the source domain. And it's also hard to estimate the density ratio. The problem itself, I'm not sure if it's even like simpler than the original problem itself. And third, this procedure might reduce the bias, but might also inflate the variance, especially if this value is very large at some points. And another type of algorithm is distributional matching. And it is done through a lot of like domain adversarial algorithms. And there are other types of algorithms that ensures that we learn some invariant representation. By invariant, it means that the representation performs similarly across different domains. However, there are actually a lot of analysis on this kind of algorithm that like forcing the representation to match might not preserve the right information for y given x. So today in this talk, I will propose the label propagation idea. So this idea is not entirely new, but there were not like enough theoretical support. And today I'm going to discuss like why and when it will work, and what changes we have done to make it work better. So is there any questions for now? Okay, then I will move on to our framework on label propagation. So as we mentioned that we have the source and target domain, and to indicate the algorithm, let's just look at this illustrating example. On the source domain, we have the data from two classes, the blue ones, class -1, the red ones, the right boss, class 1. And suppose we have a teacher classified that performs reasonably well on those samples, that it can distinguish between red and blue quite well. But as we mentioned that when it applies to the target domain, it can be like entirely wrong on some part of the data. And the main idea of label propagation is to notice that this teacher classified violates a certain important rule, which is that the data that are close to each other with similar semantic meanings should predict the same or predicts at least similar. However, in this region, let's call that inconsistent set, these are the data points that there exists some data point close to it, but your classifier just predicted entirely different. Therefore, the main idea of label propagation is to reduce the possibility of this kind of inconsistent set. And what it does is first to minimize the difference between your learned classifier with the teacher classifier on the source domain, because the source domain is where you trust the result, you trust the prediction. And in the meantime, ensure the samples with similar semantic meanings to predict similarly. In that way, on each like this components, the idea is like you realize that on the source domain, the majority of the predictor is 1. And you also want the predictions to be consistent. So you are trying to propagate the correct label 1 to the entire domain, to the entire component. So that is the idea of label propagation. But here, notice I said that we want to ensure the samples with similar semantic meanings to predict similarly. But of course, here I'm like using L2 distance to measure the semantic similarity. That doesn't really make sense. So actually, we should capture the semantic similarity in a different space. And we should build the data in a good representation space where their distance is something we trust that can capture their semantic similarities. So I will discuss how to obtain this kind of representation space with self-supervised learning in the end. But now suppose we already have such a good space, and let me just introduce its properties, because I don't want to distract you too much from the main story of label propagation for now. So let's say here we have a good representation space. It just means that we map the data from the input pixel values to a vector space that can like represent the data similarities with the space distance. Then with this representation space, we can actually divide the data into different subgroups. So again, here we have 2 classes, the blue ones and the red ones. And with data mutation and the distance in the representation space, those data are naturally splitted into subgroups. So what do I mean? For example, we have like, suppose the blue class are like the class of birds. And here we have different types of different kinds of birds. They are from different environments. Like this one has like a water background, and this one has Greenland background. And they might not be directly connected by data mutation, meaning there is not a data mutation that maps this image to this image. But they can still be like considered connected in these components, because there might exist some data mutation like random crop that crop the head part of this image and the head part of this image, and they are close to each other in the representation space. Therefore, I'm saying like these components are the data points that are directly or indirectly connected to each other with with data mutation, or they are close to each other in this representation space. And the number of those components highly depend on the strengths of the data mutation. Suppose you have very weak data mutation where you only generate one different image for each sample, then there will be like millions of components. But if you have quite stronger data mutation, then this will be like large components. Like these are components of like the black and white warbler, and this part might be a component of eagle. Is this part clear?
We're good. Thank you.
Okay. And if we are able to like split the data into the subgroups, we can actually propagate the data from like the correct labels we have with the teacher network to the other region in each component. And here I will try to present more formally the algorithm of label propagation. Let's say Bx is the set that describes all the possible data mutations of each sample X. And we will design the consistency regularization, which will help us to do the label propagation algorithm. And this consistency regularization just measures the amount of inconsistent set of any given classifier G, which means like it's the probability of each of X such that there exists an augmented data where their predictions are different. And in this figure, it will just be the probability of this dashed part. Because there exists like a data mutation or like just a small deviation on each sample, but their predictions are different. And with this kind of consistency regularization, we can present our label propagation algorithm. So as I said, the main idea is to minimize the difference to the teacher classifying the source domain while ensuring the augmented data to predict similarly among all unlabeled samples. So our idea is like this. So we'll minimize the difference of our prediction of our learned classify with the teacher classify. And meanwhile, we will ensure that the consistency regularization to be small. And this mu is a hyperparameter we want to tune. So let's suppose we have a ground truth classifier that performs consistent among all data set. For example, in this case, if there is a consistent, if there is a good ground truth classifier that is consistent among all all augmented samples, then this mu should be 0. But as otherwise, we will need this mu to be larger than the value that is given by the ground truth classifier. And our final result of the test performance will depend on this mu. Okay, then we will give the theoretical analysis. So first is the ideal case. Let's say there exists a realizable, robust classifier, which means there exists such a good classifier such that it can separate all the samples. But in the meantime, there's no consistent set, which means there's no point that when you add label propagation, when you add data mutation or like add some small deviation to it, the predictions remains the same. Then in that case, just proof by picture, you can see the main idea of our label propagation algorithm is to first realize on each like component from the source domain, this value is the majority of the prediction value is 1. And since you want to maintain that there's no inconsistent set, which means for each connected component, we should predict the same value. So in this component, it will predict all 1 value. And similarly, with this component will predict -1, etc. Then our algorithm will learn a perfect classifier if the teacher classifier is at least 51% correct on each component of the source data. And beyond the perfect case, let's relax the assumption. If there exists some misspecification, which means the ground truth classifier, the inconsistent set has the probability of mu, then this means that it's possible that data augmentation might connect two different classes by mistake. For example, you have like random crop on the belly of a cat and the belly of a dog, and they look similar. It's possible that they are connected in the representation space. But that will happen very well, so mu would be a small value, and we can still handle that point. And the main idea is like still similarly, we will take like the majority value of the source domain and propagate that to the unambiguous region, where for the ambiguous region, we will do something like majority voting. And to use this idea, we need a technical assumption, which is the data augmentation should have this expansive property. This is proposed by Wei et al. 2021. And it is saying that data augmentation can enlarge any small enough set to say times larger. And they have verified this kind of assumption by empirical validation. And more formally, it's saying like within each connected component, for any small enough set A, by small enough, I mean that the probability of this set is less or equal to this A. Then when you do data augmentation of the entire set, its probability is enlarged by C times. So this is sort of saying like the strengths of data augmentation, how much more samples can you create with the current samples. And we can show that if the data satisfies half C expansiveness, the data augmentation satisfies that, then the target error of the learned classifier given by our label propagation algorithm is upbounded by order mu over C, where remember mu is the inconsistency probability of the ground truth classifier. And if we believe mu is very small, then this value is also very small since C is always larger than 0. And of course, this value is given by like training on the probability of population risk, but the results naturally extend to finite sample result with some standard analysis. So this is like the approximation error where we'll add some estimation error with some concentration on the neural network or other function class we use. Before moving on to the experimental result, I want to emphasize this idea actually applies generally. So previously, I'm talking about a source domain and the target domain where we have unlabeled samples from both. And this is the setting of unsupervised domain adaptation. However, the idea of label propagation apply more generally because as long as the connected components of the unlabeled samples we have covers both the source and target domain, then we can perform label propagation in general. So it also applies to like semi-supervised learning, which means like the unlabeled samples we have are from the same distribution as the source and target domain. Because you see, even if the teacher network you originally have only performs like 51% accuracy, you can actually correct the teacher network and have better performance even in the original source domain. And it also applies to other settings. For example, if we have multiple domains, then multiple source domains, that is like domain generalization. Yeah. Then let's look at experimental evaluation. We are looking at two types of data set. One is benchmark data set for domain adaptation tasks. For example, with Office Home dataset, it has 4 different domains like art, flip art, to real world, and it has different classes. And we also have Office 31 dataset, and we evaluated our method and compared it with some other state-of-the-art method called MDD, margin disparity discrepancy. And we realized that by adapting from the source domain to different target domain, the performance of our algorithm is better than the previous algorithm. And another type of data set we use is entity 31 from Breeze. And it has different data set where it has a subpopulation shift, meaning that for each class, it has data sampled from different subclasses. And on this data set, we showed that our method has much better performance than the previous different methods. Just focus on the test accuracy here. Okay. So our analysis is actually based on propagating correct labels to images closed in semantic meanings. And that is measured by the closeness of two images in the representation space. And I haven't talked about how to achieve such a useful representation space yet. So now let's talk about that. The representation space we get is through self-supervised learning. And specifically, one type of self-supervised algorithm, let's call it similarity-based self-supervised learning, because the main idea is to enforce two views of the same data to have similar representations. Like if we randomly sample some image and we take random data mutation, different random data mutations, these are just two views of the same data. So we should expect their representation to be similar. And there are different algorithms that learn the representation with this kind of idea. And the difference is they design different loss functions to maximize the agreement among those representations. And they use different methods to avoid collapse. Because you see, one trivial way to enforce that the representation of this x1 and x2 to be the same is to predict all one function, a trivial function. But that's not something you want. It hasn't captured the meaning of different images. And they use different ways to avoid collapse. And this algorithm is actually the same spirit as the conventional canonical correlation analysis. Because if you recall what is the CCA or nonlinear CCA, it is trying to maximize the inner product between the representation per psi x1, inner product with another representation on x2, with the samples from their drawing distribution. And also to make sure that the representation function is normalized. So you can see it is very similar to the other self-supervised learning algorithm. We want to make sure that their agreement is maximized. The representation of this x1 and x2, their agreement is maximized. Well, the difference is they use different ways to prevent collapse. Like CCA uses kind of normalization, while SimScience is another method. It uses batch norm and stop gradient to avoid collapse. And contrasted learning, it uses negative samples to avoid collapse. But with CCA, it has cleaner statistical meanings, and we are able to analyze that. And with the nonlinear CCA algorithm, we can actually show such a very clean result. Suppose that with x1, we are able to predict the label y with high accuracy, or like the base error of the ground truth classifier to predict y given x1 is very small. Then we can actually show that the approximation error of using a linear function on the learned representation to predict y from the learned representation per psi x1 is upper bounded by mu divided 1 minus lambda k. And the lambda k is the case maximum correlation between x1 and x2. It just measures some dependence between x1 and x2. And it's guaranteed to be smaller than 1 as long as x2 and the x1 are not exactly the same. So this means that as long as we believe that with x1, the label is almost deterministic, then the label y actually can be linearly separable by this learned representation per psi x1. Yeah, so this shows that the learned representation almost linearly separates label y, and this means the L2 distance in the representation space will indicate whether two images are more likely to belong to the same class. And that explains why label propagation in such representation space is much better than propagating on the original input space. Yeah. And in conclusion, we have analyzed that consistency regularization under data augmentation not only will correct misclassified samples in semi-supervised learning, but also can propagate the correct labels to other domains with unlabeled samples. And in the meantime, self-supervised learning learns the proper metric that will aid this procedure. And that's the end of this talk. Thank you. Any questions?
Thank you, Chi. Any questions for Chi? So let me start with one. Could you say a little more about the training procedure? You wrote in the middle of the talk a constraint optimization problem, and yeah, I was wondering how you do that in practice.
Yes, that's a good point. So the actual algorithm we use, or actual method we use, there's a discrepancy from the theoretical algorithm we theoretically analyzed algorithm. So we are actually applying existing loss function with fixed match to our learned representation space. But the difference is like fixed match was designed for semi-supervised learning, and we just use their designed consistency regularization to our problem and extend it to this domain adaptation problem with unlabeled samples from the target domain. And we also like apply it to the representation space. That's the difference. Yeah, but the actual loss function we use are not exactly like this. Yeah, sorry. Not exactly like this. This you cannot estimate efficiently. So the actually consistency regularization is like we sample we have the sample the batch of samples and minimize the difference between this prediction and the augmented samples prediction.
Thank you. I think Grant, Shafi has a question.
Just in the beginning, you said that the whole approach is to solicit more data, right? In order to be able to handle the distributional shift. So maybe I missed it, but where is that come about? How much more data? That was in the beginning, in the first 2 slides or something. I think you said that.
Yeah. So you mean this? Like we need additional data, right?
Yeah. So what is the quantitative?
Yeah. So in the traditional supervised learning setting, we only have labeled samples from the source domain. Here we assume we have additional unlabeled samples from the target domain.
But I'm asking how much?
Yeah. How much? You mean like in theory or in practice?
I mean in theory.
in theory, our analysis actually assume we have like free access to the unlabeled samples.
So you cannot, so if you have n examples in the training, is it sufficient to have n examples in the testing, I mean, afterwards, or do you need more than that?
Sorry, I didn't hear there.
Could be more than the amount of training with its labeled, or the same amount?
Oh, yeah, in our analysis, the unlabeled samples are much more than the labeled samples because they are almost free to get. They are unlabeled samples. Yeah, we didn't actually analyze the sample complexity for unlabeled samples.
So just to continue the question, how the...
Could you use the mic,
yeah, sorry. Just continue the question, how does the unlabeled data appear as a performance to the rate in comparison with the... I think it's a lower order.
You mean like how does the amount of unlabeled samples appear in the result? Right?
Yeah, somehow it should appear, right?
Yeah. Our analysis actually suppose we have like the free access to all the unlabeled samples, so it doesn't appear. So it's only a statistical result. So not about like tractability or like optimization efficiency. So it's saying that we only analyze the sample complexity for labeled samples. We didn't analyze sample complexity for unlabeled samples, so it doesn't appear.
I guess I was wondering. I just want to ask a follow-up on the same thread. Like, is it possible that you generate this data yourself, these additional samples? That's what I understood at some point, but.
To generate the data.
I don't know, can you generate some fake samples that kind of look like they could be from that distribution, or maybe it doesn't make sense in your setting? I don't
know. I think that's a very good idea, and many people are doing that. Like you can like change the background. You split the data with foreground, background, and change the background. That's how people are creating different domains artificially. Yeah, that would be a good idea, but not necessarily related to our setting for now.
I think Grant had a question that quickly flashed on the. Is Grant there? Maybe Grant can unmute himself and ask the question. I think the question was along the lines, what are your next steps in this line of work?
I see. Yeah, so as you guys have mentioned, that's a very good point that it's worthwhile also to analyze the sample complexity for unlabeled samples. That's one thing. And also here, I only analyzed the covariate shift for classification task. But because you see, like with classification tasks, the label are just is discrete. There are two values. Or with regression, it might be harder, but still possible. That could be a next step. And also other types of distribution shift, like modal shift.
Thanks.
Yeah. Thank you.
I guess I was wondering, like, I guess I'm probably missing some details, but like, in principle, you could imagine that in many applications, you can continuously move in the space of inputs or possible inputs to go from like any pair of animals to like any animal to any other, like, you know, you have birds on the trees and then, you know, squirrels on the trees and then this and like what, like, I wonder, like, do you want to be in a situation where kind of like most of your connected components are pretty clearly a certain label? Like if you're in a situation where kind of like all clusters, you know, are consistent with two labels, you know, or not all, but like every cluster at some point gets one label and at some point other point gets another label. Like, is that breaking down your framework here, or?
Yeah, so yeah, actually, like
a preconditional thing of your theorem at least was that this doesn't happen very often, this disagreement.
yeah, exactly. So I think we should like balance this two. So if you have like super strong data augmentation that can connect any class to another class, I would say that's a data augmentation. The meaning for data augmentation is you shouldn't change its original semantic meanings.
Yeah, I guess what I'm afraid is like rather than cropping the feathers of the bird, you instead crop the trunk of the tree. And then, you know, in a different picture, the same trunk of a tree has a squirrel on it. And then, you know, all birds and all squirrels and this stuff like that may happen. So, but yeah, I see your point. So
yeah,
there must be some augmentation that doesn't kind of like connect the whole space.
yeah. So we also handle that, but you should make sure that this probability of connecting two classes to be small. Otherwise, there's no like ground truth classifier either. So,
Gotcha.
I mean, ground truth robust classifier.
All right. So if there are no further questions, let's thank Chi again.
Thank you.
All right, to see you all